Swayam Prabha. Digital India. Educated India.
Okay, dear students, today this class I will teach you the limit of detections and wasp-free biosensor. So last class I taught you different techniques like cyclic voltammetry, coulometry, chronoamperometry. Now using this technique we have to find out the sensitivity, how sensitive this biosensor. Huh? So we have to understand the calculations, like how we can calculate the sensitivity of the biosensor. Then next topic I will go to the wasp-free biosensors. This is a very important technique of biosensor, so that we can apply this novel technique for point of care device development that I will teach you today. So our main concept we will cover today, the limit of detections, that is the very parameter, just very basic things. Then I will cover wasp-free and its optimizations, its design used for the biosensor development. Okay. So the main keyword of this teaching was the wasp-free technique and point of care diagnosis. Another thing you can consider the limit of detections. These keywords you can search and you will get lot of information for the biosensor development. Okay, now let's come the biosensor, how we can use this one by using our whatever you learned last few classes. Then apply your knowledge of cyclic voltammetry, amperometry and coulometry and detect the signal. Okay, suppose you have a transducer surface, right, and this transducer surface is modified with avidin. Why we need avidin? To modify the primary antibody, right? Because avidin and biotin, they have strong interactions. Your primary antibody already conjugated with your primary antibody is conjugated with the biotin, right? Your biotin. So avidin biotin has strong interaction that I already taught you. So this is just for conjugation chemistry, and we will drop the sample. Here is the sample. So if you drop the sample, then your target will bind with your specific antibody, and then drop your secondary antibody that I taught you. The secondary antibody already have the tag like gold nanoparticle, and then you can use some chemical substrate, and that can react to form the product, and that will release the electron, right? This is the very basic biosensor. Now get the output. How we can measure this output? Just last class I taught you, different technique. Let's use those techniques. So this is just for your applications of your technique. So just I want to apply cyclic voltammetry. You can remember this is the cyclic voltammetry technique, where in the x-axis is the potential window, and we applied here. See, we mentioned silver chloride. Silver chloride is the reference electrode, because we are applying some potential with respect to some reference electrode. Which reference electrode? That you have to mention here always. So E versus AgCl. So an unit is the volt, and y-axis is the current, where unit is the microamps. As I said, if this chemical is formed like a very good reversible redox process, like Fe2 plus, Fe3 plus, they are very reversible reaction. In this case, you will get this kind of cyclic voltammetry shape, voltammogram, like it would be like this. But if it is not like a reversible reaction, something irreversible, suppose you have glucose, as I mentioned, so in this case you will get something like this, or some substrate. If the oxidations is not favorable much, then you will get something like this. So in this case we use some chemical, the oxidation is favorable, but reduction is not that much favorable. Okay. Okay, done. Now I will come how we can measure this electron. See, in the cyclic voltammogram case, we will scan in a potential window like 0.2 to 0.4, and we will measure the different potential, we will measure the current. See, when you oxidize from the negative potential to positive potential, the current increase, and then it's become like this. Now, if we increase the target concentration, what happened in the sensor surface? What happened when you increase target concentration? More target means more gold nanoparticle will be on the surface. So, more gold nanoparticle means more chemical will react, will form the more product. So, more product means more electron. So, your current of the cyclic voltammetry will increase. See, so as you increase the concentration from this to this, when you are increasing the concentration, see, the current also slowly increase, right? So, your cyclic voltammetry helping you to get the output in the form of the current with respect to potential, and by using this current, you can determine the concentrations of the target present on your biosensor surface. How? So, you can make a calibration curve basically by using this cyclic voltammetry. This is just in the form of current. Now, make a calibration curve. I will make calibration curve. Calibration curve will be something like this. In the y-axis, you are getting the current, right? So, y-axis your output current microamps. In the x-axis is the concentrations of your target, your target concentration, that you can put in the x-axis. So, let us measure the all the current with changing the target concentrations. Okay. So, from here let us move. Suppose in the 0, so you have to fix a potential. Suppose at the 0.1, so 0.1 volt in this potential you want to measure all the current. So, 0 cases you are getting this much current, in the 100 femtogram case you are getting this much current, and 1 pico case you are getting this much current, and 10 pico case you are getting this much current, right. So, this all the current you just measure and plot it. Suppose 0 case you are getting here, 100 case you are getting here, then 1 case you are getting here, and 10 case you are getting here. Sure. So, something like this. So, then you can make a something like this a calibration plot, but not one data. Then it is rule at least you have to make a 3 data for each concentration. Then you have to check the error bar. For one concentration you have to make 3 sensor surface to get the reproducibility. To get a reliable sensor, at least 3 sensor same concentration you have to make, and you have to see they are reproducible or not. So, 0 cases just you have to check like 3 times, like by measuring 3 different electrode surface. Same case like 100 femto, 1 pico, 10 pico, every case you have to make 3 electrodes. But especially we favored 0 data, your basic data, right. Then we are taking sometimes 7 times also 0 data, so that at least your base value should be more reproducible, right. It should not be like up and down, then it will be difficult to obtain the sensitivity, means your limit of detections of your sensor. That is why we are measuring more data of the 0. Then we are getting the some error value. This is the error value, error bar. And if you make the straight line something like this, so you can see your full calibration curve with different concentrations. So, this is called calibration. This is your output value by using cyclic voltammetry. Now, suppose you have a sample, a unknown sample you have, unknown, suppose you use here blood sample. So, you have a one unknown blood sample, you do not know its concentrations of target, that you do not know. So, how will measure? Let us drop this sample here and measure, just run a cyclic voltammetry, and suppose your cyclic voltammetry came here. So, how much current you are getting in this potential? Suppose here 0.5. So, suppose this one here. Then you just draw a straight line up to this line, then draw again the straight perpendicular line. Then you can measure your unknown concentration. Okay, this much. So, this much your unknown concentration. So, by applying your calibration curve, you can determine your unknown concentrations of a solution. Okay. So, this is just for using a cyclic voltammogram technique. Now, let us use chronoamperometry, let us use the chronocoulometry, all the technique now I will teach you. I will show you. This is just for one example I will show you. Then next I will come the another topic. Okay. So, for getting the detection limit, here I am showing the another example. This is what is this unit, this technique. Remember, here in the y axis we are using charge, x axis with respect to time. So, this is chronocoulometry, right. So, we are using chronocoulometry with different concentration of the target. Let us go back. So, here we use the cyclic voltammetry with changing the concentration, and here we are using this chronocoulometry with respect to charge and time. So, 0 data here, now change the concentration 10 pico, 100 pico, 1 nano, 10 nano, 100 nano, right. Like this way we are increasing the concentration. See, we are increasing the, what we are increasing? Charge we are increasing. Why charge will increase? Because you are using something like this biosensor, a sandwich biosensor, sandwich ELISA type of biosensor you develop. So, if you increase the target, so more nanoparticles will form on the sensor surface. More nanoparticle means more product will form, you will get the more electron on the surface. So, charge will increase. See, that is why charge we are increasing. And you measure here, see, this is the calibration curve. Calibration curve. So, based on this output, based on chronocoulometry. So, based on this output, we measure this calibration curve. So, for that you have to just fix a time, like suppose 60 seconds. In the 60 seconds, we will measure all the charge. All the charge we will measure for each concentration. See, for the each concentration, suppose in the 60 seconds we fix all the charge, and which this concentration case we are getting this much charge, this concentration, this concentration, this concentration, and we measure three times. That is why we are getting this error bar. Each concentration we measure three times. Okay. So, if your sensor surface is very reproducible, then this error bar will be very short, and your sensor will be most reliable if this error bar is very short. Okay. Now, let us come the detection limit. This is a very important parameter to understand your sensitivity of your developed biosensor. Let us teach you the detection limit. So, what is the definitions of the detection limit? Detection limit is nothing but this is a whether we can detect a molecule in a certain limit, like it will show you the acceptable value your sensor can detect. This is the lowest amount you can detect by using your biosensor. That is the LOD. It is called limit of detection or detection limit, LOD. The detection limit can be defined as the smallest amount of the concentration of any analyte or in your test sample that can reliably we can distinguish. See, so from this biosensor we can see that we can determine 0, 10 like this way. Then we made a calibration curve. So, in this calibration curve you can see we put all the concentration, all the different concentrations. So, this is the 10 pico, then 100 pico, this is 1 nano, 10 nano, 100 nano. In this case you are getting this much charge. Now, here I did not put the 0 data, I put the 0 data something like this way, and we put plus 3 SD. So, what is this? Let us understand this one to calculate limit of detection. Okay. So, as I mentioned, your 0 data is very important to get the limit of if you want to develop very good biosensor or very sensitive biosensor, your 0 data also should be very reproducible. That is why sometimes we are not measuring 3 times also 7 times you can measure. Means 7 times means 7 different, means 7 sensor you have developed, means similar your 0 data sensor you can develop, then measure there all the 0 data. Suppose in the 0 like chronocoulometric 0 data you are getting this like this way, charge versus time, like 7 data it can be like this. So, there is some deviation there. So, this error bar we have to calculate. means standard deviation. You have to calculate from here standard deviations of the 0 data. 7 0 data you can measure and calculate the standard deviation. And you can multiply with these 3. So, maybe your standard deviations of your 0 data is here, but we are multiplying with 3, then it come here. So, why we are multiplying 3? To minimize the human error. So, see, suppose I am developing a biosensor using all the protocol. So, I am getting this much 0 current, 0 background, that is a background current, right? 0 data case. But you are developing and you are getting maybe something different, little bit different. So, it depends, man to man, sometimes it can vary also. Okay. So, to minimize this one and to make the most reliable sensor, so we are multiplying with this 3 and see, and this 3 times standard deviation, this is the mathematically proof, mathematically acceptable if we can multiply with 3, and see it come here, and then it will decide your sensitivity of the biosensor. See, this 3 times standard deviation, now it already tasked with your concentration that detected with 10 picogram. So, we cannot go below of this concentration with your biosensor, because this value already touched your 10 picogram per ml concentration, this charge value. So, this one will be your detection limit, because it already touched. Generally, what we are doing, so let us remove this thing. We are actually making a straight line. We are making a straight line by using all this concentration, and where it intersect this one will be your LOD. Okay. So, you cannot go below than this, because it is already touched this line, and if you make the straight line and this already touched, this is your limit of detection. But if you have one calibration curve, suppose I want to show you, suppose you have calibration curve this one, maybe here, right, maybe this concentration here. So, you have some gap with this 3 times standard deviation, then you can go below of this concentration, that will be your limit of detection. This is not your limit of detection if it is up of this line. But if suppose you have one biosensor and it can measure, means it can measure 10 picogram per ml. Here you can see here you can see difference. Here 10 picogram ml, here it is showing the difference, but after calculating standard deviation, multiplying with 3, everything, but your 3 times standard deviation line here and your 10 picogram per ml, this charge is point is showing here, then this is not your limit of detection. Then you have to actually make the straight line, and if it cross here, this will be your standard limit of detection. This is not your limit of detection. Okay. So, you have to first measure the 0 data, you have to make the standard deviation and multiply with 3, and then you have to make this base straight line. This will guide you to determine the limit of detection. So, this one, the lowest amount you can detect, that this parameter detection limit will guide you. Okay. So, this is the whole things, these informations we are getting from this limit of detections, this parameter, and we can determine like this way. Now, I will show you one more example of limit of detection by using the cyclic voltammetry that I taught you already before. So, last class I showed you just a chronocoulometry, but here just a cyclic voltammetry. I think I already mentioned, see, in this case, in the cyclic different concentration, we are getting different cyclic voltammetry, like 1, 2, 3, 4 different cyclic voltammetry we measure. Now, other data I didn't show you. So, in this case, you can see you can measure so many other concentrations also. So many other concentration, you get the cyclic voltammetry something like this, and you have to fix a potential. So, here is a fixed potential like 0.035 volt. In this potential, we can measure all the current, and all the current you can put here with respect to the concentration. So, this is called the calibrations, and then you have to determine the standard deviation of the 0 data and make this value, and then make a straight line, and where it intersect, that will be your limit of detection. Okay. So, like this way we can determine. So, this thing is done, limit of detection this part, I think it is very clear to you. Now, I will show you some biosensor where we can use this all the concept to determine the limit of detection and use this all the cyclic voltammetry, coulometry, amperometry, all the cyclic voltammetry, chronocoulometry, chronoamperometry, all the things we will use. Okay. Now, today I will show you one more important technique for point of care device development, that is washing free biosensor or immunosensor. So, this washing free immunosensors is very important to develop a point of care device. What it is washing free? As I mentioned, when you develop some biosensor, you need many steps washing, right? On the primary antibody surface, then maybe you have to drop a your target, then you have to wash it, then secondary antibody that conjugated with the label, then you have to wash it. But that cannot be done by end user, right? If you want to develop a device for point of care, maybe for field testing, so end user cannot do this all the steps. That's why you develop, if you can develop a sensor that is wash free, just drop the sample and you can get the value. That will be very impactful for the point of care device development. Let's come the principle for this wash free device development. Okay, so let's remove this. I will now show you one by one steps. Okay. So, washing free technique, this is the very important, where all in one means all the reactions will happen on the sensor surface. We don't need any extra steps. Suppose you have a like this a sensor surface that already modified with some primary antibody. That where I use the avidin and biodenylated antibody, this conjugation protocol. Now, what I will do, in a sample tube, I will put your all the chemicals like secondary antibody, we need some substrate, we need some mediator, everything I will put on a sample tube. And here also I will drop, here also what I will do, I will drop my target solutions. Target solution. So, this is your target. I will drop the target solution. Now, I will drop these solutions on the sensor surface. Okay. What will happen? What will happen if you have the target? This will bind on the sensor surface, right, with primary antibody, and your secondary antibody that is already labeled, that also will bind with the target, right? And all the other chemical like substrate, mediator, here AOX is the ascorbate oxidase, one chemical that can react with the ascorbic acid and it will remove the ascorbic acid by reactions. So, why we need ascorbic? Because ascorbic acid is very means bad, it is a interfering species that can increase the background current. So, we have to remove them. So, that is why I use the AOX that will react with ascorbic acid, will remove. So, all the chemicals I will use in this sample tube, I will drop it here, then reaction will start. See, your sandwich already formed on the sensor surface, and now if you have the chemicals everything, then you can apply the redox cycling reaction, like EN means enzymatic redox cycling, because your tag is an enzyme. So, you can apply enzymatic redox cycling. See, so here M plus means your mediator oxidation state, M means your mediator in the reduction state, like ruthenium 3 plus, ruthenium 2 plus, something like this. So, your substrate product like glucose, it is glucose oxidase, they will react, right. So, this kind of redox cycling reaction will start on the sensor surface. And if you have don't target, see there is two part in this sensor. In the left hand side, if you have the target, in the right hand side, if it is zero data, like if you don't have target. So, if don't have target, then your secondary antibody that conjugated with the enzyme, that will not bind on the sensor surface, right. If you target, then it will bind, right. So, when you apply some potential on the sensor surface, about 0.3 volt you are applying, and you started the redox cycling reaction, these redox cycling reactions will start in the left hand side, that will be very fast, that will be very fast. Why? Because it is very close to the sensor surface, it is called a close, it is called proximity dependent. This is proximity dependent electron transfer. So, this redox cycling electron transfer, because of the close proximity, it will be very fast. but in the other case it will be very slow because it's far from the sensor surface. So this electron transfer rate will be slow. So easily, that's why you can differentiate target and zero data, like signal and background data. You can easily differentiate because of this proximity dependent electron transfer rate is the different. Clear? So see, here I am not using any washing, just we drop all the chemicals here, then we are applying some potential and we are getting the difference. Why it is we are getting the difference? Because of this principle, proximity dependent electron transfer, this difference, this principle we are applying. See, so this actually basically you don't need any extra steps of the washing steps. That's why it significantly can reduce the detection protocol and detection time. You can develop a sensor surface, there will be just a sample zone you can drop, and you just apply some potential using some portable potential stat, and that's done. Maybe you can wait for 5 minutes for antigen antibody interaction and you can see the value. So this kind of washing free sensor is really impactful for development of point of care device. That's why. So I will show you this kind of wash free sensor can be useful very chip based or lab on a chip based biosensor, like something like this. I want to show you one basic, very basic example that's reported in this journal. You can see here your primary antibody coated your 3 electrode system, right? Reference electrode, working electrode, counter electrode. This is your 3 electrode system, and upper of this antibody coated working electrode surface, you can use few membrane, that is paper based membrane you can use, where you can use all the chemicals. So here maybe some ruthenium based chemical, here some methane blue, or maybe a secondary antibody. So here also some chemicals you can use for redox cycling formation to get the ultra sensitive biosensor, right? All the chemicals I taught, we need some different chemicals for ultra sensitive biosensor formation. So those chemicals you can keep here, all the this membrane. Now we can drop the sample. Okay, so if you drop the sample, then suppose it is blood sample. But blood contains so many blood cells. You have to separate all the blood cell. So here we can use a blood cell separation membrane. So it will remove all the cells. Then you will get all the plasma. So this plasma will go through this all the reagent. So this all the reagent will dissolve. Your primary and your secondary antibody, everything will come and they will form now this kind of sandwich ELISA on your sensor surface. Clear? Now you can apply the potential. Here you can apply the potential and you can see the output. Maybe in the form of cyclic voltammetry case, you will get output something like this. Or if it is chronoamperometry, then you will get the output something like this with different concentration. You can see different value you can see, and based on the calibration curve, you already have a known calibration curve, right, that I told you, and based on the unknown solution, you can determine the unknown sample concentrations. It is very, and that everything we can make a mobile phone based sensors. So your all data, like your all the calibration data, everything will be stored. And we can make IoT enabled biosensor, and in an app all the information will be stored, and this how much current is generating via Bluetooth, it can send to your mobile phone. Okay, then this current is corresponds to how much concentrations it can automatically it can predict, and it will show on your app display. You can see, okay, so if it is like malaria, if you want to detect, so it can show you how much malaria present in the blood samples. You can see easily. So like this way, you don't need any sample pre-processing, you don't need many step sample handling, mainly you don't need any expert persons. By developing something very simple sensor surface, you can use this one for point of care device development. So this is, so here I use some wash-free technique, wash-free biosensor, this is called, that's why, and that one will be useful. It's very small chip also you can develop. It can be useful for point of care device development. Okay, so in the next class again I will show you like different optimization parameter, how we can optimize. Like here I showed you the principle of the voice-free biosensor development, but just principle I taught you today. Now let's find out how we can optimize a voice-free sensor. There is a different parameter, existing parameter are there. So we have to optimize all the parameter because there is, otherwise we can face lots of interference effect. Maybe your signal and background we cannot differentiate if we cannot optimize all the parameters. That is very important things. So next class I will teach you all the parameter selections and how we can optimize. Okay. So that's all for today. So here I just taught you the voice-free development, signal measurement systems, and this will be very much useful for point of care diagnosis. Okay. So thanks for today, and next class I will teach you the optimization for voice-free. Thank you very much.